Welcome to the Calculus BC video for skill number 229. I can apply differentiation rules within the context of rate of change. And the trivia question for this video is below is featured a topographic map of a geographic feature called a saddle. And if you're familiar with topographic maps, they're a way of representing hill and slope of hill. And the trivia question is, given the drawing below, could you sketch an arrow on it that points uphill? Alright, so this skill has lots of different ways that it could be presented or asked on the skill test or on the AP test. So I'm going to work through one very thorough example, which is we're looking at a question similar to what you'd see on a free response, maybe the first half of a free response question, leaving out the latter half requiring some later stuff in calculus. First, let's quickly go over some quick notation. Average rate of change can be found by calculating the slope of this secant. So if you had something like this, you can find the average rate of change between those two points by finding the slope of the secant. And the most common way would be to take y2 minus y1 over x2 minus x1. Or we notate it in function notation, f of x2 minus f of x1 over x2 minus x1. More common to calculus would be actually finding the instantaneous rate of change. And let's circle these in red. The instantaneous rate of change would be the slope at a point. So we want to know the exact slope at that point. So what we're going to do is, we've seen the notation dy dx. So what we're doing really is we're taking the limit as our delta x, or our change in x, approaches 0. So we're taking these 2 points and they're getting closer and closer together until the change of them is a distance of 0. So that's instantaneous rate of change, and we're going to focus on that concept today in this video, talking about the movement of a particle. Now it should be noted there's lots of different ways we could talk about rate of change, and we'll try to hit some more of those in our assignment. But for our particle movement, there's some stuff we should know. If we let s be our position function, or f of t is our position function relative to time, then our velocity is the derivative of the position function. So velocity is ds dt, or you could say f prime t. And consequently, we can also find acceleration. So our acceleration is dv dt, which is the second derivative of s, or f double prime of t. So the question I'm going to pose is, I'm going to give you position, and I want you to find the velocity and acceleration, and do various things with that information. Here we go. They give us a position, and what it looks like is we have a cubic function, and we're first asked to find the velocity at time t. So that's pretty much straight up find the derivative of f. So we apply the power rule to each piece. The derivative of t to the third is 3t squared. Derivative of minus 15t squared is minus 30t. And the derivative of 48t is just 48. So velocity is the derivative of position. And then they ask, what is the velocity after 1 second? So that's simply plugging 1 into the velocity equation. And then again, what is the velocity after 4 seconds? And we plug 4 in. And we notice that one of them has a positive velocity and one of them has a negative velocity. And those mean different things. So we're going to get into that. When is the particle at rest? So a particle's at rest if the velocity is 0. So we're going to take our velocity function and we are going to set it equal to 0. And I notice it's a quadratic function, so in solving it for equal to 0, the approach I took was factor out the greatest common factor and then factor the quadratic expression. So we find that v of t is 0 at time 2 and at time 8, which means our particle will be moving along, and then at 2 seconds it stops moving along, and then it'll start moving along again. Maybe it changes direction, and then at 8 seconds it stops and probably changes direction again. We're going to get into drawing the diagram in a short bit, so don't draw it yet, because it may not quite look like that. When is the particle moving forward? So what that means is, when is the velocity positive? So our velocity was positive at 1 second, so we know at time t equals 1 it's moving forward. But what's that window? And 2 and 8 provide us the points where it stopped, so we can say before 2 it's either moving forward or backward, and then it changes directions, and then after 8 it's moving either forward or backward. So we know at time 1 it's forward, so this is forward, and then it goes backward, and then it goes forward. So it's changing directions at time 2 and 8. And we could actually evaluate just to be certain. We could say, what is the velocity of 1, what is the velocity of 3, and what is the velocity of 9. And we'll find that we have positive, negative, and positive velocities. So we know those intervals of time give us forward, backward, forward. So if we wanted to draw a diagram of that, we know at time 0 it is traveling forward all the way until time 2, and then from time 2 to 8 it's traveling backwards, and from time to 8 on it's traveling forward. If we want to get some relative positions, we could plug in at time 0 what is f of 0, so it gives us a value of 0. At time 2 it gives us a position of 44, so from here to here it traveled 44 meters. And then at time 8 it's at negative 64, so from time 2 to 8 it traveled the 44 meters to get back to the start point, and then continued on to negative 64 meters. So a total of, what is that, 108 meters backwards, and then it changed directions to go forward again. So if we're asked to find the distance traveled in the first 15 seconds, we need to break it up into each piece moving forward and backward. So the first piece we found was it moved forward 44 meters from time 0 to time 2. We can take the position at time 2 and subtract the position at time 0. If we take the absolute value of it, it gives us a total distance. Then from time 2 to 8, we do the same thing. We take the position at time 8, subtract the position at time 2, and we get the total distance traveled once we take the absolute value of that. And it says for the first 15 seconds, so now we need to go from time 8 to time 15. And we find that f of 15 minus f of 8 is 784 meters, which means the total distance traveled is the sum of those three values, which is 936 meters. And the last piece, it says find the acceleration at time t and after 6 seconds. So the acceleration is the derivative of our velocity function. So we can take our velocity function, which is on the back page, 3t squared minus 30t. And if we take the derivative of that, we get 6t minus 30. And if we want to know the acceleration after 6 seconds, we just plug 6 into our acceleration equation, and we get 6 meters per second squared. Alright, thanks for watching the video. And if we wanted to draw arrows that go uphill, this is uphill and this is uphill. So working to our saddle, we go uphill to this point, and then we can go further uphill to that point.